Let's look at this particular activation energy problem using the Arrhenius equation. We're asked to calculate the activation energy for a reaction that doubles its rate, which essentially means the K value doubles when we go from 25 to 35 degrees Celsius. If you remember, as a rule of thumb, the rate should double every 10 degrees Kelvin or 10 degrees Celsius. This is only true if the activation energy has a particular value, and that is what we are asked to calculate. So with two temperatures and no value for the frequency factor, then it just makes sense to use the most recent form of the Arrhenius equation that we introduced. Natural log of K2 over K1 equals negative EA over R multiplied by 1 over T2 minus 1 over T1. If we remember, the rate is directly related to K, so if the rate doubles, then K doubles. Then we could say that K2, the rate constant at 35 degrees Celsius, is 2 times K1. Although we don't know K1 or K2, we can put in for K2 2 times K1. This allows the K1s to cancel. We can then plug in our temperatures, remembering to convert them to Kelvin, and rearrange our equation so that we can solve for activation energy. Remember, because R is in units of joules per Kelvin mole, when we are all done, EA will be in units of joules per mole. However, often activation increase is expressed, once calculated, in units of kilojoules per mole. So, doubling the temperature, increase in the temperature by 10 degrees Celsius doubles the rate if the activation energy is 53 kilojoules per mole. It turns out that for many reactions, the activation energy is right around 53 kilojoules per mole, so 10 degrees Celsius increase or 10 degrees Kelvin increase results in doubling of the rate. Most activation energies are on the order of close to 0 up to about 200 kilojoules per mole, with right around 50 being common.